Welcome to the lectures on modern digital communication techniques. We have been discussing source coding, and what we have covered till now is unique decodability, prefix-free codes, craft inequality, and finally we have come to understand a mechanism by which one could encode a discrete source. So, of course, we are talking about discrete sources. So, while doing it, we have come across several ways of doing the compression in some way, or we are finding out that what is the average number of bits per source symbol that you need to send. So, when we did it, we wanted to also find out that this average number of bits per source symbol that we are getting, what is the minimum value of it. And when we did it, we used the craft inequality because we had to set the prefix free condition, and the reason for doing so is we wanted to have the unique decodability criteria. So, when doing it, we used the Lagrangian method and we relaxed the integer length constraint, and when we did it, we found that you could choose lengths L for a particular symbol j to be equal to the ceiling function of log base 2, the minus sign of Pj, where Pj is the probability of occurrence of the jth symbol. So, with this we had shown that if you select symbols in this way, then the number of bits that you get is indeed very close to the entropy, where we defined entropy as the measure of the minimum number of bits that is required to encrypt the source. So, if this runs over G, then P of j log base 2 P of j, the minus sign in front of it, and this gives a measure of what is the average, on an average, minimum number of bits required. And when we did this particular method, we found that these are integer numbers. So, only when this Pj was equal to some integer power of 2, we realized that this could be the actual minimum, and when it is not, then it is more than the entropy, but it is at most 1 bit more than the entropy, and this bounds on entropy we had established in the previous discussion. So, we said that L bar min is less than Hx plus 1 and is greater than or equal to Hx. So, this is also something which we had established. So, and we took one particular example in quick passing, that this may not the method of finding or the using this particular expression is not always going to give the best result, and we look at a counter example where we said let the probability of 0 be p to the power of 2 to the power of minus 10, and we will see another example today. So, further we said that if these what you need to look at is rather encode n tuples. We had seen this thing for fixed length code, and we had also shown that if you have variable length code, then also you can come arbitrarily close to Hx. So, at that point we said that L min bar when taken n tuples at a time is very close. So, you get a tighter bound 1 upon n and Hx. That means, by choosing n very large, you can make it very close to Hx. This is all that it says. So, if you are going to take n tuples at a time. So, when we did n tuples, what we meant is that if you take a few symbols 1 to up to n symbols and encode them, in that case on an average you are going to get this particular situation. So, this is a fixed length code, because from fixed length words you are mapping to variable length, and then only you are establishing this, because we used for establishing this we used h of x n, that means the entropy of a discrete memoryless source for n tuples is n times Hx. So, this is what we had used and we had arrived at this result. So, we move on further with this basic background, and let us see that what can we get out of this. So, with these let us start off by considering a source which generates a 0 or a 1. So, this particular source is a binary source. So, if it generates a 0 and a 1, then we need to characterize the source, and as mentioned before, that the source characteristics can be described by means of the probability of occurrence of one of the symbols, and we say for our particular example let it be 1 upon 4. Since there are only 2 symbols, definitely this p of the second one is 1 minus the probability of that. So, p of 1, the probability of getting a 1 is 3 upon 4. So, for this particular source, what we would like to find is find a suitable encoding scheme. Now, this might seem to be a very simple task. So, before we proceed to find a suitable encoding scheme, what we would like to do is try to find out what is the entropy. So, if you are interested in finding the entropy, you would calculate H x going by this expression. So, that will be minus 1 upon 4 log base to 1 upon 4. So, it goes up minus 3 upon 4 log base to 3 upon 4. So, of course, this minus comes in, 4 by 3 minus goes in, it is 4. So, this part is very easy, it is 1 by 4 times minus. So, 4 goes on top, log base 2 of 4. So, that is 2 to the power of 2, 2 comes outside, log base 2 of 2 is 1. So, you have 2 minus, sorry, there is a plus, let us say, you can't help it here, you have to look into the log table. So, you are going to get 0.415, and this is actually half. So, if you evaluate this is almost 50% of 0.34. So, what you get is nearly 0.81127 as an answer, that what you would get, and this is definitely bits per symbol, right. So, this is what we can start off with. So, if we take this, the next simple thing that we have, we do not have much option in this. We have a 0, we can encode 0 with a 0 or a 1, and if you have 1, you have no other option but to encode it as 1 or 0. So, whether this is 0 or 1 and this is 1 or 0, it is the same story. So, we have this. So, if you take this source coding, that is, you are basically doing nothing, you are allowing the source to pass through almost as it is, or it is one of the simplest possible source coding, 0 becomes a 0 and 1 becomes a 1. So, there is no change. So, these are the symbols, and these are the encoded bits. So, what we have, one symbol mapping to 1 bit, one symbol mapping to 1 bit. So, therefore, we can say that you have 1 bit per symbol. All right. So, if this example is a bit confusing because you have 0 mapping to 0, we have a simple thing. Let's talk about a source where there are only 2 possibilities, A and a B, right. Another simple source could be black and white. So, we can take a screen or a page which has only black and white dots, and a black would be represented by, let us say, 0, and a white could be represented by 1. So, if that is the case, then all these things become very clear, that we have a black which could be mapped to 0. So, this would be equivalent to this 0, and this 1 would be equivalent to this 1. So, in this case, you can similarly say that the black gets mapped to 0 and the white get mapped to 1, that is it. So, what we are asking is what kind of coding you can do. So, this is the coding which you did, and you can get 1 bit per source symbol. Let us proceed a bit further with this example, and if we have to take this solution, that we have mentioned earlier. If you have to take this solution, then let us see what do we get. So, if we do log base 2 1 by 1 upon 4, because you have a minus here, that means log base 2 of 1 by Pj. So, which we can write okay. So, we are using that, simply that expression. So, this is very, very clear. So, this is equal to 2, and if we have to use the ceiling function of 2 is basically 2. So, that means L for let us say black is basically 2. So, this means 2 bits, it says, this says you use 2 bits to represent black, and if I have to represent white, which comes with a probability of 3 by 4, right. So, that is the same example that we have. So, of course, what we said is P of black is 1 by 4 and probability of white is 3 by 4. So, log base 2 of 1 upon 3 by 4, and you take the ceiling function. So, that is the ceiling of 0.415. Now, since I cannot take 0.415 bits, I have to take the nearest integer. So, length of white should be equal to 1 as per the solution of this, that is the method to find the minimum number of bits. So, going by this, if we have to construct a code tree, we can construct a code tree, one branch and of course, the second one here. So, this one I could label as white, this one I could label as black, 0 1 0. So, now going by our earlier discussion, since you can clearly see that one branch can be added, it is not a full tree, and also this branch could be reduced and brought over here, right. Still it does not violate the prefix tree condition. That means, there is although this appears to be an earlier intermediary node, but we can shorten the tree and then the code becomes 1 for black, 0 for white, or vice versa. We could have drawn the tree otherwise. So, this is superfluous, we do not need this. We can actually do better by simply sticking to our original encoding scheme, this one or simply this encoding scheme. So, well, this really does not help us at this point, and in fact, if we try to calculate the average. So, if we try to use this method, let us say, what we are going to get is 2 bits coming with a probability of 1 by 4 plus 1 bit coming with a probability of 3 by 4, and this will be 1.25 bits, which is definitely worse than this, which is 1 bit per symbol. All right. So, now we clearly see that L bar, this is not a good solution that we have arrived at. So, instead what we can do is, now we can consider let us use a different technique, and we say that if you remember what we studied earlier, that you can actually take n tuples. So, if we take n very, very large, then of course, we can reduce this excess. So, what we do as a first step, we can take two symbols, right. So, this black we can take. So, basically if I take 2 symbols, the first place can be filled in 2 different ways, black and white, second place can be filled in 2 different ways, black and white. So, we basically end up with 4 possible options. So, we could have a black and a black, a black and a white and a black, and a white and a white, right. So, this forms my new symbol, super symbol, black black or black white or white black or white white. So, if we take these 4 symbols, then we can encode this new source. So, as if this source generates a symbol which is black black, which generates another symbol, could be white black or black white, or could be white and white. So, these are the 4 distinct symbols that it generates. So, since the source is a discrete memory less source that we have taken, that means the second symbol is independent of the first symbol. So, the joint probability of this would be product of the individual probabilities. So, this probability of occurrence of this symbol is simply the probability of occurrence of black times the probability of occurrence of black. So, this is 1 by 4 times 1 by 4. So, this is 1 upon 16. So, we could write these as symbols, and we could write this as probabilities, right. So, by doing so, we can calculate the probability of getting a black followed by white, which is 1 by 4 of black times 3 by 4 of white. So, this is 3 upon 16. By the same logic, this one is also 3 upon 16, and getting white and white is 3 times 16 times 3 times 4 3 upon 4 times 3 upon 4, that is 9 upon 16. So, these are the probabilities of each of the symbols, and if we have to calculate the lengths, that is L j. So, j is equal to 1 in this case, j is equal to 2, j is equal to 3, j is equal to 4. So, we have these 4 symbols that are there with us. So, LJs following this, it will be 4 bits, okay, and this particular case, so this result is straightforward. If you evaluate this, you are going to get 4, a ceiling function of 4 leads to 4. If it is 3 by 16, so basically log base 2 of 3 by 16 or log base 2 of 16 by 3, this is ceiling function of 2.4. This you will be landing up definitely with 3 bits, because 2.4 bits you can't do. Same over here, 3 bits, 9 upon 16, this turns out to be 0.83, this results in 1 bit. So, what we have in this case is we are trying to encode this new symbol set with these lengths, right. So, if we are going to do it, of course, we can find out whether it satisfies the Kraft inequality, but what we have seen earlier, that if we follow this method, it is definitely going to follow Kraft inequality. That means, we can ensure prefix free codes. So, that is why we looked at the theorem, and therefore, we do not need to do it again, but for your own sake you can easily calculate. Okay. So, right. So, we can do this, and therefore, we are going to get, we can construct a tree and we can make codes, but what is our interest as of now is to find what is L bar. So, L bar is the average number of bits per source symbol. So, the way we calculate is we are going to get 4 bits whenever BB comes, but BB comes with a probability of 1 upon 16, and every time it comes we are going to get 4 bit. 3 bits are going to occur with a probability of 3 by 16, because this is going to come with a probability of 3 by 16. Every time we get 3 bits, we get it 2 times, and this one is going to occur with a probability of 9 by 16. So, we are going to add up only once. So, when you add this, you will get the answer of 1.9375. Now, if you look at L bar is with 2 bits, right. So, please remember this is with 2 bits. Okay. So, what is L bar per symbol? So, L bar per symbol would be L bar of this. So, I would rather say L bar 2, I would not put a 2 over here. L bar 2 would be this divided by 2, and this turns out to be 0.9 6, 8, 7, 5. So, what you can see is earlier we were having 1.25 bits if we followed this raw expression by taking one symbol at a time, and which is worse than the case if I would directly encode it, which is 1 bit per symbol, which is also represented here. But now, if I have clubbed two symbols, that means I have formed an n tuple where n is 2, I could reduce the average number of bits per symbol. I could reduce that average number of bits per source symbol to 0.96875, and this is definitely less than 1, right. So, as we move further, of course, we just need to remind you that we had found the entropy of this system to be 0.81127. That means, we have been able to come a little bit closer to this number. So, moving ahead further with this, you could ask what would be the case if I take 3 symbols as a tuple. That means, if I let n is equal to 3. So, if n is equal to 3, since each position can take 2 values, that means, each position can take a black or a white, 2 possibilities. So, definitely you are going to end up with 8 possibilities, right, and then you can do a similar calculations. And what we can do now, instead of doing for 3, let us take the case if I am going to take n is equal to 4, right. If I take n is equal to 4, of course, I have 2, 2, 2, 2. So, 2 to the power of 4 possibilities, and that would be yeah. So, if I have there would be 2 possibilities here, 2 possibilities, 2 possibilities, 2 possibilities. So, I am going to get a much a smaller number in this case, right. So, as we move ahead further, you can possibly get these numbers which are smaller than this. Yeah. So, with this, if you go ahead and consider a particular example where we say that suppose I have a 2 gigabyte file to transfer. So, suppose I have a 2 gigabyte file to transfer, and I use this particular method of encoding as we have just discussed. So, what is there any benefit? So, what you can calculate is that if you do not do this, you would send 1 bit per source symbol multiplied by 2 multiplied by 8 multiplied by 10 to the power of 9 bits altogether. Whereas, if you are using this encoding scheme as we have just discussed here, if we are going to use this encoding scheme, then we would be saving 1 minus 0.96875 bits. So, this much of saving is going to happen in this overall file size. So, if you do this, if you work out these calculations, you will almost get 0.5 gigabits. Please note, I have used gigabytes over here, but I am converting to gigabits. And if we do the calculation that say we have a 10 Mbps line, suppose I have a 10 Mbps line. So, I would require 0.5 into 10 to the power of 9 bits divided by 10 into 10 to the power of 6 bits per second, lesser time if I use this particular method. So, this would result in 0.5 into 10 to the power of, so this and this would cancel out to make it 100. So, I am going to get nearly 50 seconds or roughly 1 minute less time to download this particular file, and which is significant. And if you look at this particular number, then you can guess the number of bits that get saved. So, if you are thinking in terms of the subscribers, so one generally has to pay in terms of number of bits. That means, finally, you go in for a package of like, let us say 500 megabyte or let us say 2 gigabyte for so much of sum of money, let us say 100 rupees for 1 gigabyte, something like that. So, in this case you are saving quite a bit of data if you are doing some data compression. And if you are thinking in terms of speed or download time, if this kind of data compression is done, then again you can save quite a lot in terms of bandwidth. That means you can free up the channel for at least 1 minute in this particular example that we have taken. So, I hope this helps you to realize that if you do this kind of an encoding, and of course many other advanced encoding schemes, then you could have a huge potential in utilizing the spectrum or the bandwidth much better than if you do not do any kind of source coding. So, let us move on further and try to look at another situation. So, where let us say we have the problem that we have 3 colors, red, blue and green, and we say that red comes with a probability of 1 by 4, blue comes with a probability of half and green comes with a probability of 1 by 4. That means, let us say I have a screen and or I have an image where every pixel in that can take one of these 3 colors and only one of these 3 colors, and I would like to encode this picture in this pixel and send it out to the other side. So, clearly since there are 3 symbols, so going by our previous notation, m is equal to 3, and if you have to use some fixed length code, then you have to take log base 2 of 3 and a ceiling function of that, which would result in 2 bits. So, clearly you can say that I would encode red with a 0 0, a blue or a green, let us say green with 0 1 and a blue with 1 1. Red comes with probability 1 by 4, green comes with probability 1 by 4 and blue comes with probability half. In this case we clearly see that you have 2 bits for every symbol, 2 bits for blue, 2 bits for green and 2 bits for red. So, 2 bits per symbol. For this particular case, if you would calculate Hx, this I leave it as a home exercise, you are going to get the number as 1.5 bits per symbol. So, this clearly leaves us with a gap of 0.5 bits. Now, if it is 0.5 bits per source symbol, so you can clearly estimate that the amount of saving that you can get if there is a 2 gigabyte file that requires to be transmitted. Now, Hx, please note, this gives us an indication that what is the best possible source coding that you can achieve with this. So, well, if you use fixed length, you are in this situation, and what you could do, that you could go for variable length coding. If you go for variable length coding, since now you have these probabilities, so this would result in the code word length of 2 bits, this would result in a code word length of 2 bits, this would result in the code word length of 1 bit. So, I do not need to define what is j any further. So, and if you would like to construct the code tree, you can easily construct a code tree like this, where this will be blue, this will be green and this will be red. So, 1 1 0 0. So, blue will have the code of 0, green is going to have the code of 1 0, red is going to have the code of 1 1. So, if you do this, then you will find that if you calculate L bar for this, what you are going to get is blue comes with a probability of half, that means this code word length comes with a probability of half. So, you are going to get 1 occurring 50% of the time plus a code word length of 2 occurring 1/4 of the time plus code word length of 2 occurring 1/4 of the time. So, that is half plus half plus half. So, that is 1.5 bits. So, what you can see is that by using this mechanism you can achieve 1.5 bits per source symbol, and one can easily go back and calculate the number of bits that one would save if one had to transmit a file which is as big as, let us say, 1 gigabit or 1 gigabyte or 2 gigabyte. So, through these examples we have tried to establish how you can take advantage of the source coding schemes in order to reduce the number of bits that require to be transmitted. So, this helps you in saving the number of bits and also saving bandwidth, and beyond that you can also imagine and extend your imagination or calculations in real terms of the amount of power that it saves, which we should be able to calculate towards the end of the course. When we so basically there you use the terminology number of or the amount of joules that is expanded or that is spent in sending one bit. So, if you can find that number, let us say p joules is required to send one bit. So, and I have to send I have saved, let us say, nearly 1 gigabit. So, you can easily calculate the amount of energy that can be saved. So, it has multifold implication if we can do source coding appropriately. We stop this lecture at this particular point and we continue with these examples in the next lecture.